Hello, Cal 2. This is the first video of Exam 3 material. The good news is Exam 3 is over way easier stuff than Exam 2 was. Exam 2 was like the hardest stuff in the course. Exam 1 wasn't super easy either. Exam 3 is, I guess, easy might not be the right word for it, but it's more plug and chug type stuff. There's some formulas that you need to know. I guess bigger than formulas, there's some like concepts that are tricky to visualize, but by and large it's way easier than learning how to write math, which is part of what was going on in Exam 2. We start by talking about parametric curves. Here's the idea of a parametric curve is sometimes we mostly do calculus on the situation of y equals f of x. But there are times in life that you want to talk about a thing, a graph that is not a function of x. How can you talk about this? How can you think about the slope of this line if I can't use the word derivative because it's not a function? The idea of a parametric curve is that instead of using x as the parameter, we introduce another parameter. Usually it'll be t for time. The example we're going to do in a second will be, we'll use a different letter for another reason. But so on and so on. Instead of thinking about the curve as just a shape, we introduce this other parameter. So now this description is not unique. I could move along the same path faster or slower and get a different parameterization. But the key thing is that every point, if this is t equals, what is that, like 60 or so? The coordinates of this point will be x is a function of t and y is a function of t. Our function is no longer one function, but two functions. A formula for what is your x coordinate and what is your y coordinate. The coordinates of this point, if this is 1, 2, 3, 4, 5, if this point is 3, 5, then we're learning that the x coordinate at time 3 is 3, and the y coordinate at time 3 is 5. Instead of one function, we have two. And this lets you get around most of the complaints you have about being forced to work with a function. That's the idea of a parametric curve. To deal, and a heads up, it's super nice that this jumps very easily into space. If I want to talk about a curve moving around in space, which we won't talk about much in this class, but the idea works easily. You just throw in a z-coordinate, and now you have a curve moving around in space instead of two-dimensional space. Let's try working out an example of this. I like starting with the example of a cycloid. The idea of a cycloid is we set this circle down on the x-axis, a circle with radius 1. We pick a point on the circle to label red, or I'm grabbing red. And the idea is I want to roll that circle along. And as it rolls, that point on the circle is going to move. As I've rolled over here, the point might be up here, and then it'll be up here, and maybe eventually it gets up to here. And I want to ask myself, what is the path that that point travels as the circle rolls along? Maybe maybe I attach a pen to the side of the circle. Is there a way to build this in real life? Take a can, put it on the floor, stick a paintbrush or a marker on the edge of the can, and roll it parallel to the wall and ask yourself what is the path that the paintbrush draws as the can rolls around. It's pretty easy to imagine. It's going to go up and down. So this thing started at 0 on the y-axis, and it's going to go up and then it's going to go down. The circle has a radius of 1. So it's pretty easy to work out the perimeter of the, what do they call it, the circumference, that's the word. The circumference of a circle is 2 pi r is 2 pi, so the circle will have to roll a distance of 2 pi. After 2 pi is when the dot goes back to the floor again. Halfway up it's going to be at the very top. In between, it's sort of unclear what's going on. There's a good chance, I can imagine that it's going to have a horizontal tangent at this point. Like there's going to be a cusp there, maybe? Because if I think about the circle rolling, this thing is kind of going to be lifting straight off of the ground at the very start, right? It'll move a little bit to the right, but its general motion is going to be up. There's very little sideways motion component. Anyway, we can check that out. Here's the idea. We want to come up with an equation for this. And it turns out the easiest way to do this is parametrically. The question I want to ask myself is, if the circle has rolled a little bit, how far is it rolled? Like, I want this distance to match this distance, so my thing should be around there. What's a good way of figuring out the x-coordinate and the y-coordinate at this point? Well, you've taken a trig class, so you're pretty good at understanding things in terms of angles. If I label this angle theta, we're going to use theta as our parameter. We're going to figure out what's x as a function of theta and what's y as a function of theta. The thing that always helps me is redraw the unit circle in the standard position. If this angle is theta, then this thing and this thing get names. This will be cosine theta, and this will be sine theta. And now I want to take this standard orientation unit circle and imagine I have to like rotate it and reflect it so that theta is measured in the correct way. But this distance and this distance are things that I care about, are functions of theta. And what is it? If it was normal standard, this distance is going to be called sine theta. And this distance is going to be cosine theta. Have I done this right? I'm too dumb to imagine moving a circle around. Don't get old, students. Can I rotate? No, rotating doesn't work here. If I spin it this way, so I'm measuring it this way. Yeah, so rotate it 90 degrees clockwise, and now theta is going to land here, and this thing will be sine theta, and this thing will be cosine theta. Okay, now when I reflect that across the y-axis, that's sine theta, and this is cosine theta. Okay, yeah, I think I did this right. Okay. Cool. So what are the coordinates of this new point? Well, its x-coordinate is this distance, right? One of the tricky parts is I need to know what is this arc length. For a circle of radius 1, arc length is theta, and that arc length is important because that's going to be the same as this, because that's what rolling is the distance that the wheel has moved around the floor is the distance of the floor that you've traveled. So this distance is going to be theta, and this distance we just said is sine theta. So our new x-coordinate, x of theta, I just said it was going to be x of t, but it's traditional to use theta for this one because, you know, it's an angle, not time, although the angle is measuring time passing. X of theta is theta minus sine theta. Theta minus sine theta. What's our y-coordinate? Our y-coordinate is go up by 1, circle has radius 1, and then down by cosine theta. So it's 1 minus cosine theta. Hey! We got an example of a parametric curve. Cool. A thing you might stress about is the way I drew this picture only makes sense for if theta is in quadrant 1, but it's pretty easy to work out that for any other angle, the same thing will apply, and it'll be the same formula for if you're in other quadrants. When sine theta and cosine theta go negative, the same formulas will tend to do the correct thing for you. What are some questions we want to be able to answer? I guess the very basic one is what's going on at different points in time. Like, let's plot a couple points. X of theta, y of theta. What's going on? Hey! I think we're back. Okay. I think we're streaming again. Sorry about that. I don't know what happened there. What were our formulas from a second ago? X of theta is theta minus sine theta. Okay, my stylus is not working at all now. Or it's only working... What? I think I need to start a new video. I guess before that, I need to figure out how to get my stylus to work again. I can change the battery on it, but that doesn't seem like the issue. Maybe there's something in this... I'm changing the battery, because that's the thing I know how to do. I don't really expect this to work, but sometimes weird things happen. Nope. What happens if I hold this button down? Nope. I think I'm going to end the stream and try and figure this out.